questions, you do put it in the chat box, and then those who have questions can stay back and we'll try and discuss. So then next we go on to measures of association. Now here, when you say measures of association, there are two different types of measures. One is ratios and the other is absolute differences. Now the ratios like your odds ratio, risk ratios, those ratios measure what is known as effect of exposure on outcome. And the absolute differences which are there, when you subtract one from the other, that is a difference that measures the impact of the exposure on the outcome. So you have to be careful with these words when you are using in your studies. So when you are just calculating ratios, you should say the effect, I am studying the effect of the exposure on the outcome. And if you are going to calculate and interpret attributable population attributable risk, which is where you're subtracting one from the other and looking at differences, that is the time you will say I'm looking at the impact of the exposure on the outcome. Another important thing to remember is that this effect, once you calculate effect, you cannot directly calculate at the same time the impact. Once you say there is an effect of the exposure on the outcome is present, you have to go through the criteria of causal association and prove that this exposure is a cause of the outcome. And after proving causal association, only then you should calculate the impact, that is these absolute differences or absolute measures of impact of the exposure on the outcome. Are you getting me here?
Yes, ma'am.
Yeah. So the effect, when I say I want to study the effect of the exposure on the outcome, I am looking at these ratios, which are relative measures of association. They are looking at multiplicative effect of the exposure on the outcome. And the answer they are telling us is how many times more the exposed have the risk of the outcome compared to the unexposed. It tells us about the strength of association and the effect of exposure on the outcome. And when you're looking at causation, one criteria is strength of association. That value comes from these ratios. It can be a prevalence ratio, a risk ratio, a rate ratio, or a hazard or a odds ratio. So when you have, say, a risk ratio of 2, you say the risk of the outcome is twice or 2 times higher in exposed as compared to the unexposed. Compared to the effect, when you come to impact, so you have shown that there is a significant effect of the exposure on the outcome and all other criteria of causal association seem to hold true, then you can move ahead with calculation of the absolute differences between the risk in the exposed and the unexposed. So these differences are the what are known as absolute measures of association. They tell us the additive effect of exposure. The answer which they tell us is how much more risk do the exposed have as compared to the unexposed. So the ratios were telling us how many times more risk is there, while the differences are telling us how much more is the risk in the exposed as compared to unexposed. These estimates are telling us how much of the outcome is attributable to the exposure, either in the exposed group or in the population. So all of the outcome is not attributable to the exposure. Certain percentage of that is attributable to the exposure. So how much of that risk or the outcome is attributable to the exposure is what these differences tell us. While the effect measures, the ratios, when you divide one by the other are important in causal association, the differences are important from the point of view of public health and policy making. So what these differences tell us is, supposing the risk difference is 0.10, it tells us that the exposure is going to increase the absolute risk amongst the exposed by 10 cases per 100 people. So whatever number of cases are there in the unexposed people, 10 more cases are there in the exposed people. Per 100 people, there are 10 more cases in the group which has exposure as compared to no exposure. So this is the difference between the two measures. You begin with the effect, and then if you are able to prove effect causation, you can then subtract the incidence in the exposed from the unexposed, and find out how much more risk is there in the exposed as compared to the unexposed. We all are very well versed with these ratios. So you all know that if you can calculate the cumulative incidence, you can calculate the risk ratios. If you can calculate the incidence density, then you calculate the rate and you calculate the rate ratios, which is also many a times reported as relative risk. So these ratios were all common. I'm sure you all know that if you get a value of 2, a relative risk of 2, how do you interpret the relative risk of 2? How do you interpret a relative risk of 0.8? And then you all know about the importance of the 95% confidence interval, the null value, whether it's included in the 95% confidence interval or not, and the fact that how confident you are that the true population value lies within the confidence interval. So all these concepts we are well aware of. What I'm going to focus on is this impact thing, which is the absolute difference. That is answering how many times more the risk in the exposed as compared, sorry, how much more the risk in the exposed compared to the unexposed. So in this particular table, what you are seeing is that the incidence per lakh population per year in the smokers and non-smokers. So in both the groups, if you look at the ratio, which is the measure of effect, the effect of smoking on lung cancer, it is 10. So smokers have a 10 times higher risk of lung cancer. If you look at the relative risk for ischemic heart disease, you will see that the smokers have 2 times higher risk of IHD as compared to non-smokers. So you can see that the smoking has a very, very strong association with lung cancer. And it is 2 times higher in IHD, but not as strong as for lung cancer. So when you calculate relative risk, you have an estimate of the effect. Then you look at the causal association, and smoking appears to be causally associated with both of these outcomes. You go a step ahead and you calculate absolute difference. What is absolute difference? It is the difference of the incidence in the exposed minus the incidence in the unexposed. And what do you see here? You see that the absolute difference, that is how much more risk in the smokers is there for lung cancer, it is 9 per lakh. While for ischemic heart disease, the absolute difference is far higher as compared to lung cancer. So it is 125 per lakh. So the concept of absolute difference or the impact is very different from the strength of association or the effect. That is what I'm trying to show you in this particular table. So for lung cancer, the strength of association was more. But when you look at effect, the effect of smoking appears to be more for IHD than for lung cancer. So the impact is more for IHD. The effect is more for lung cancer, but the impact is more for IHD. So these two are different concepts, and I'm going to talk a little bit more. So people ask me about books, reference books. So all these concepts about risk, absolute risk, difference, population attributable risk, all these are given very well in Gordis. So do read Gordis, because these are given with wonderful examples and figures, and it's very, very easy to understand. So what we see here is that this particular thing which you see here, this is the incidence or the level of risk in the exposed and in the unexposed. So the concept is that not all of the risk in the exposed is because of the exposure. So there is some background risk, which is this risk which is happening in the unexposed. So if you subtract this background risk from the entire risk in the exposed, then you get to know exactly what amount of risk in the exposed is attributable to the exposure. This is known as attributable risk. That is, in the exposed, not all of the outcome is because of exposure. So whatever outcome in the unexposed is there, that you consider as background risk, and you subtract it from this risk, whatever remains is the risk which is attributed to the exposure in those who are exposed. You are getting me here?
Yes, ma'am.
Yes, ma'am.
So this is something which you need to read up, that from this particular book, to understand what is known as attributable risk. So this is a formula, that is, now instead of dividing, you are subtracting the incidence in the exposed minus the incidence in the unexposed. So if the incidence in the exposed is 0.02, incidence in the unexposed is 0.01, you are going to divide and subtract, and you're going to get 0.01. So this means that for 1,000 smokers, there are going to be 10 additional cases of IHD compared to the number of cases which are there in 1,000 non-smokers. So how many additional cases, extra cases are there in the exposed, is what the attributable risk tells you. And usually what you do is you calculate not attribute, or you at least report attributable risk percent. That is what I showed you in the graph. So out of the total risk, so risk is incidence, out of the total risk in the exposed group, what percentage is because of the exposure? Subtract the incidence in the exposed from the incidence in the unexposed. So you know what proportion of the incidence in the exposed is because of the exposure. That is known as attributable risk percentage, or etiologic fraction, or attributable fraction in the exposed. So supposing you get attributable risk percentage of 50%. So what does this mean? This means that 50% of the outcome, that is the ischemic heart disease, among the smokers is due to smoking. And if smoking is given up by the smokers, there will be a 50% reduction in the ischemic heart disease amongst the smokers. So attributable risk is telling us what percentage of the incidence or risk in the exposed is because of the exposure. Are you getting me here?
Yes,
Yes,
ma'am.
ma'am. Yes, ma'am.
Okay, then I'll quickly move ahead. Now, this is an alternate formula for attributable risk percent. So if you just divide both the numerator and denominator with incidence amongst unexposed, you get this formula. So why I'm telling you this formula is, if you are given a problem, or if sometimes you just have the relative risk available with you, still you can calculate the attributable risk percent. So all you have to do is you subtract 1 from the relative risk and divide it by the relative risk, and you get your attributable risk percent. So if relative risk was 2, you would do 2 minus 1 upon 2, which is 50%. So you don't need to know the incidence. Just by a single number of relative risk, you can calculate attributable risk percent. I'll quickly move ahead. Now, attributable risk tells you the proportion or the percentage of the risk in the exposed which is attributable to the exposure. But for those who are implementing program or policy makers, they are interested to know how much amount of the risk in the total population is attributable to the exposure. So here you have to calculate what is known as population attributable risk. So the population consists of people who have exposure and who do not have exposure, both. And population attributable risk is equal to the incidence of the disease in the total population minus the incidence of the disease in the unexposed divided by the incidence of the disease in the total population. What does this mean? This means that out of the disease in the total population, that is your denominator, incidence in the total population, what percentage of the disease is attributable to the exposure. Now, these people are interested in this because what this means is that if the exposure is withdrawn from the population, what percentage of the disease will disappear from the population. So by what percentage there will be a decline in the outcome in the total population if the exposure is removed from the population. That is what. So policymakers, you can give them some like direction about or motivation for taking up initiatives for people to give up the exposure or to remove the exposure from the population by convincing them about the percentage decline in the disease if they are able to successfully remove the exposure from the population. Are you understanding this?
Yes, ma'am.
Yes, ma'am.
So here is an example again, because I am not really focusing on examples, but just conceptual understanding. So if you have 60,000 subjects in a population and there are 800 cases who develop IHD over 10 years. So you have the incidence in the total population. What you want to know is incidence in the unexposed who are there. Now your exposure could be, say, smoking. So if you subtract the incidence in the total population minus the incidence in the unexposed and divided by the incidence in the total population, you get 25% as a population attributable risk. What does this mean? This means that 25% of the ischemic heart disease in the total population is because of smoking, and it can be prevented if people give up smoking in the entire reference population. So when you are interested in the what is happening in the population, you need to look at the incidence in the total population and calculate population attributable risk. Now I am telling you this is because just to understand the difference between attributable risk percent and population attributable risk percent. The simple thing to remember is that in attributable risk percent, you find out the percentage of the risk which is attributable to the exposure among the exposed. But in population attributable risk percent, you are interested to find out the percentage of the risk in the total population which is attributable to the exposure. This is what you need to remember. And this is again from Gordis. This is very well given. Please go through this chapter and you will understand these concepts clearly. So remember that if you are given a 2 by 2 table, you can calculate relative risk, you can calculate attributable risk as well as population attributable risk by making some assumptions with the formula which I have given you. There are a few formula I'm going to tell you later on also, but for the population attributable risk, if you don't know the exposure in the population, then you can take whatever you have, the values which are there in the total population for the exposure and the outcome, and use it in your solution. So if you are given a 2 by 2 table with whatever data is there with some assumptions, you can go ahead and calculate your relative risk, attributable risk, as well as population attributable risk. So try doing this and with those assumptions using the formula which we have discussed. Then in incidence, remember I told you, will you have any problems or will you be able to solve this? Try doing it. And if you have any problems, you can put it up in the WhatsApp group. Now we are talking about incidence, right? So in incidence, whenever we are doing a follow-up, you are able to calculate the incidence. Then what is the role of the case control study? Because you must have seen I had mentioned odds ratio as a measure of strength of association or the measure of effect. So how does that come into the picture? So remember that in a case control study, usually you will do case control study for rare diseases. You take the cases, usually all the cases or a representative of all the cases from the study population. And how do you choose your control? Now there are some criteria for choosing the control in the case control study. These controls should be representative of the population which produce the cases, and the reason why you're choosing your controls is because you want to capture the exposure, the distribution or the kind of exposure which is there in the population which produce the cases. So these are important statements about a case control study, because in a case control study, remember what is happening in a case control study, you are choosing cases and then you are choosing some controls. So there is no denominator in a case control study. right? Like in your cohort study or in your intervention study, you know that out of these many individuals, these many cases cropped up. So these many were exposed, these many were not exposed, and out of these many cases came up in the two groups. But this is not happening in a case control study. You are choosing cases from the study population and you are choosing some controls from the study population. You do not know the base or the denominator here. So you cannot calculate your incidence here or even your prevalence in a case control study. Please remember, you cannot calculate the prevalence nor the incidence in a case control study. All you can calculate is the odds. The odds. Now, in a case control study, what you calculate is the odds of exposure in cases. So what are odds? Odds are nothing but probability of the event happening divided by the probability of the event not happening. So what is the probability of exposure in cases? It is A upon
C.
C, very right. And probability of no exposure in cases is C upon A plus C. When you divide one by the other, A plus C gets cancelled. So the odds of exposure in cases is nothing but A upon C. So if you will read in books that the concept of odds is difficult to understand, it is difficult to communicate, right? And therefore, that is a big limitation with odds and odds ratios. But if you understand here that what are odds, it's nothing but dividing probability of something happening divided by probability of it not happening, then you will understand that if you know the formula for probability, you divide one by the other, you will know that odds of exposure in cases is A divided by C, and odds of exposure in controls is B divided by D. And then your odds ratio is odds of exposure in cases divided by odds of exposure in controls, which gives you a cross product ratio, which is AD upon BC. Are you getting me here?
Yes, ma'am.
So you have remember that these case control studies which are done for rare diseases and you are going from the disease to the exposure, these cases are sampled from the population. The controls are also coming from the population. You do not know any denominators. All you know is cases, and then you're taking a history of exposure from the cases and controls. So you begin by calculating the odds of exposure in cases and control. Odds are nothing but probabilities of event happening upon not happening. And when you divide, then the odds of exposure upon in cases upon controls, you get the odds ratio. Another thing to remember is that the odds of exposure is equal to the odds of the outcome. So when you're doing case control studies, once you get the odds ratio, it doesn't matter whether you say that the odds of the exposure in the cases was so many times more compared to controls, or you say that the odds of the outcome was so many times in the exposed compared to the unexposed. Both are equally acceptable. So there are no assumptions and no worries when you make those statements. This is something which you need to remember. Any questions here? If you have questions, do put them in the chat box. Then we have this example of a case control study, which we have discussed with our postgraduate students. Again, I am showing this. Please have a look at it. And the question is about calculation of odds ratio, about calculation of attributable risk and population attributable risk percentage. Now, all of this can be calculated using for a 2x2 table using the data which is given with some assumptions. So the next few slides are actually showing you the solution. So odds ratio, you all know the formula for odds ratio. It is AD upon BC. Now you can calculate the attributable risk percent or the attributable risk proportion using this formula. Now whenever the disease is rare, so rare means usually some books say it is less than 10%, some say it is less than 20%. When the disease or the outcome is rare, your odds ratio is equal to relative risk. So you can use this formula of odds ratio minus 1 upon odds ratio to calculate the attributable risk percentage. So when you have the attributable risk percentage of 32% for this association of prenatal irradiation and childhood leukemia, you know that 1/3 of the leukemia in the children is attributable to prenatal irradiation amongst those children who were exposed to X-rays in the antenatal period. So you can do this for a case control study. Similarly, you can calculate the population attributable risk percentage using these formula. So again, see, you are given a 2x2 table, but still you can calculate your population attributable risk percentage. I'm going to show you two formulae. I think, yes. So please remember these two formulae which you can use in case control studies. The first one you can use in any kinds of study where you should know the prevalence of exposure in the population and the relative risk. That is known as the Levin's formula. And there is the second formula, which is the maintenance formula, which is used for case control studies. So those who are interested in, going through these formulas and applying them and even using, you can use them for studies. You will see that there are studies which are published using these formulas. I will show you a couple of studies. So these formulae can be used to calculate. These are for population attributable risk fraction or percentage. I'm just going to show a few studies to motivate you all to take up such studies. These are again desk-based research, secondary data which can be used. Now, this is a study which is looking at population attributable risk fraction for tuberculosis. So what is the percentage of TB which is attributable to undernutrition or undernourishment is what this study was looking at for different studies. So these are high burden countries and they are looking at population attributable fraction. So how much amount of incident TB can be attributed to undernourishment in these different countries? What do you see in this table? Anyone can volunteer to describe what they're seeing. I've already put in some arrows. These arrows are actually showing two scenarios, a country where there is a very low population attributable fraction, only 5%. What does this mean? 5% of the incident TB cases are attributable to undernutrition or undernourishment in Brazil, while more than half of the incident cases in Zimbabwe are attributable to undernourishment. So why do you think this difference is there? Another point which you should note is in the title, if you read carefully, they have used a relative risk of 3.2, which is a strength of association. Can anyone interpret the relative risk of 3.2 in this association? You have to quickly give an answer because the 1 hour limit is I am already crossing. Relative risk of 3.2 means, see, quickly.
3.2 times the risk is increased in those having TB. Undernourished. The risk is increased
Yes,
for TB.
yes, yes. So the risk of TB is 3.2 times more in those who are undernourished compared to those who are not undernourished. So they have taken a RR globally, at the global level, they have taken a RR of 3.2. Then this formula which I gave you earlier, those formulas they have used because they have taken data about prevalence of undernutrition in these countries and they have calculated the population attributable fraction. So the relative risk is the same. Now, what they are assuming is that relative risk is a biological phenomenon. The way undernutrition increases the risk of TB is going to be the same for all human beings. So what remains? Why is then the population attributable fraction different? It is different because the prevalence of exposure is different. So you should remember that how does attributable fraction differ from population attributable fraction? Population attributable fraction is affected by the prevalence of exposure in the population. So you will see that all those countries where undernutrition is high, the population attributable fraction is high, even though the relative risk is the same. Are you getting me here?
Yes, ma'am.
Yes, ma'am.
And
Yes,
then
ma'am.
if you look at India, you will see that in numbers, India is probably the highest. The number of incident TB cases which are attributable to undernutrition are highest in India, though the attributable fraction is only 25%. Why? Because India has the highest incidence of TB. More cases are there. So though PAF is 25%, you will see it's the maximum cases. So this is a study which has used secondary data about relative risk, about prevalence of the exposure, and they have their study which they have published. And this is an Indian author. This is another study which is reporting on population attributable fractions. Now they are looking at the trends in 3 decades, which they are calling as epochs. So you have the 1990s, the 2000s, and the 2010s. And they're looking at population attributable fraction for cardiovascular disease. What do you see here? Do you see any pattern for? So again, what is it? If you see the y-axis, what you are seeing is the proportion of the risk of cardiovascular disease in the population, which is attributable to these different risk factors. So in total, if you look at all the risk factors to this extreme right, you will see that you have this is the extreme right, which is showing you the all of these, how many? 1, 2, 3, 4, 5, 6 risk factors. They are contributing to how much? So you will see that in the first 2 decades, more than 50% were attributable to these 6 risk factors. But in the 2010s, you are seeing that less than 40% is attributable to these 6 risk factors. Any other pattern you are observing with regards to these risk factors? That is, what percentage of cardiovascular disease incidence is attributable to each of these risk factors globally? Do you see any pattern? What do you see here?
Hypertension is the
Yes.
right.
So in the first 2 decades, hypertension was the number 1 risk factor. But what are you seeing? In the last decade of their study, you see that smoking has overtaken hypertension. So the proportion of the risk which was attributable to hypertension got reduced, and it was overtaken by those who were giving a history of ever smoking. So there are studies which are using the secondary data, and they are calculating population attributable fraction and are having an impact on the decisions which are taken at global or even at national level. The next thing I want to just quickly go through is vaccine efficacy. This, I think, is the last concept, second last one. So quickly, if anybody can tell me, in COVID-19, there were so many vaccines which are coming in the market. So Covishield declared they had 76% vaccine efficacy, Moderna's 96%, Covaxin 78%, and Pfizer 95%. So what does this mean? Vaccine efficacy of 76% for Covishield. What do you understand by this term? 76% vaccine efficacy. Anyone? Anyone can volunteer.
Ma'am, it's the
Yes.
formula.
Sorry, Anjana. Please repeat, Anjana. I
Ma'am,
could not.
the formula is it ma'am, incidence among unvaccinated minus incidence among vaccinated divided by incidence among unvaccinated. Like the disease
Yes.
which
So how
has
do you interpret
happened.
76%?
Ma'am, efficacy means can I?
Yes, yes, please.
Yes, ma'am. So compared to people who are not vaccinated, people who are vaccinated have 76% lesser risk of developing the disease.
Okay, right. So what I want you to understand is that 76% vaccine efficacy does not mean 76% protection. Or when somebody says that the efficacy of this vaccine is 95%, It does not mean that if 100 individuals are vaccinated, 95% are going to be protected. That is not vaccine efficacy. Both Anjana and Siva have given excellent answers, and you should understand and you should be able to communicate in simple language with the community about what does vaccine efficacy actually mean. So this comes from the concept of preventive fraction. So when you talk of attributable risk, it is when the risk is more in the exposed as compared to the unexposed. But when you're doing an intervention study, your interventions are going to be protective. So the incidence in the intervention group is going to be probably less as compared to the placebo or the standard treatment group. So in these situations, you have to calculate what is known as preventive fraction. For example, physical exercise is protective against ischemic heart disease or anything which is protective preventive. The relative risk, wherever the relative risk is less than 1, we know then that factor is protective. In those situations, you calculate preventive fraction. And as Anjana rightly mentioned, it is incidence of the unexposed minus incidence in the exposed divided by incidence in the unexposed multiplied by 100. And this is what is your vaccine efficacy. So this is a concept which is very, very critical and important to understand. Now, this is an example I have taken where the efficacy of a new, supposing there is a new cholera vaccine in the market and the incidence in the exposed is 0.01 and the incidence in the people who do not get the vaccine is 0.1. So you will calculate the preventive fraction or the vaccine efficacy as the incidence in the unexposed minus the incidence in the vaccinated. So unvaccinated minus vaccinated upon unvaccinated, which gives you a value of 90%. So this is the efficacy which is given by the company, that our vaccine has a 90% efficacy in preventing cholera. What does it mean actually? It means that the risk, as Siva rightly said, that the risk of disease in the vaccinated group is reduced 90%, yes, but relative to the risk in the unvaccinated group. So this is something which you need to understand. So there is a baseline risk in the unvaccinated group. Compared to that, the risk in the vaccinated group is reduced by 90%. It is not 90% of individuals who have been vaccinated are protected against the vaccine. So we need to clarify this misconception. So again, I'm just giving an example of Covaxin here. So this is a study which was published in Lancet, and it said that 78% vaccine efficacy. Now, actually, if you look at the data, what is the data saying? That in the placebo group, what was the incidence of symptomatic COVID-19? It was 1.24%. So out of 100, 1.24 individuals were getting symptomatic COVID. And in the vaccine arm, what was the incidence of symptomatic COVID-19 for the follow-up period? It was 0.28%. So the 77% reduction in the vaccine arm is with respect to the placebo. That is something which you need to understand. Are you getting me? This is a very important concept I want you to understand.
Can you please repeat?
Yeah. See, when vaccine efficacy is reported, there is a misconception that when you say vaccine efficacy is 95%, 95% of the population who receive the vaccine are protected. That is not the case. If you look at the previous slide, it tells us that vaccine efficacy is actually a concept which is related to attributable risk percent, because here the incidence in the vaccinated is less compared to the unvaccinated. We calculate what is known as a preventive fraction. Preventive fraction is calculated by subtracting, that is, the incidence in the unexposed, which is higher, minus the incidence amongst the exposed, that is, those who are vaccinated, divided by the incidence in the unvaccinated. So when you get a value of 90% vaccine efficacy, what does it mean? It means that considering the risk in the unvaccinated group, your risk in the vaccinated group is going to be 90% less. Whatever number of cases are going to be there in the unvaccinated group, compared to that, 90% less cases will occur in the vaccinated group. But remember that this is with comparison to the risk in the unvaccinated group. It is not like in vacuum. Are you getting me?
Yes, ma'am.
Yes, ma'am.
Thank you. So please understand, and whenever next time you come across this vaccine efficacy, look at the percentage in these terms. And then, of course, there is another, because I think in one of the exams this question was asked. So please read up what is numbers needed to treat, or numbers needed to harm, or numbers needed to screen. It is a very simple concept. So what you have to do for this is just, it is a reciprocal of the attributable risk. So if you are given any numbers, if you are able to calculate the risk in the intervention group, risk in the exposed, risk in the control group, and if you subtract, you get the attributable risk. And if you take a reciprocal of that, for example, in this particular example, the attributable, so the risk in the exposed was in the treatment group was 0.10, in the control was 0.20. So the attributable risk was 0.1, so 10%. If you take a reciprocal, you get 10. So a number needed to treat is nothing but the number of individuals who need to be treated to get at least one additional, to prevent at least one additional outcome in the intervention group control compared to the control group. That is known as number needed to treat. How many patients need to be given the new drug to prevent one additional case as compared to the number of cases in the control group. This is something which is used, if you see nowadays even in the RCTs or in the screening programs, they are reporting numbers needed to treat, screen, and sometimes if there are adverse events, even numbers needed to harm. And then there is comparison between NNT, NNH, and a decision whether to take up the intervention or not. So the lower the number needed to treat, the more effective is the treatment. So if you have two interventions, you can also have numbers needed to treat for those two. And then if they are equally, other factors are equal, then the one which requires lesser number NNT will be preferred. So this is another concept which you can understand, numbers needed to treat. And if you are given, therefore, if you have values about, say, in Covaxin, you have the incidence in the vaccinated group and the incidence in the placebo group, you should be in a position then to calculate relative risk, attributable risk percent, as well as the numbers needed to treat. So what is here numbers needed to treat? It is going to be nothing but 1 divided by the attributable risk, which you will see in the formula here. And it gives a value of 105. What does this mean? That minimum of 105 persons need to be given a vaccine to prevent any extra case of symptomatic COVID in the vaccinated group compared to the unvaccinated group. And again, you have to specify for what period of time, for what period of follow-up, and this is only for symptomatic COVID-19. So NNT is specific for a specific endpoint and for a specific period. So this is another concept which you can read up, which is comparatively new, I may say, from the syllabus point of view and from the application or reporting in the studies, but it's easy to understand and read the other types of numbers which I have told you. And then this is I'm just trying to compare the different types of vaccines, and you also have to see that though you see the relative risk, the protection offered is best for Pfizer, but you will see that the number needed to treat still is much higher for the Pfizer vaccine. And this you can then, if you read up, you will see all of this also is linked to the baseline risk or the risk in the placebo. Because the baseline risk is less, the numbers needed to treat is more. So all of these concepts about NNT especially is something which you can read up, because all of this is linked to your attributable risk, which is linked to your relative risk, which is linked to your incidence rates. So in the end, I just want to say that remember that effect, impact, first measure the strength of association and then calculate the impact. The effect is important from causal association point of view. From etiological research, they are relative measures, while your impact or your differences, that is attributable risk and population attributable risk, are important from the public health point of view. So these are crucial differences, and you cannot calculate your population attributable risk before you confirm causal association. So I just stop here and then I take questions.